Here we are, section 7.5 on geometric sequences. Here's a journal. Remember, you have to do a journal this chapter, so make sure that you take note if this is one that interests you. Here we go. Do you remember what an arithmetic sequence is? That is the list of numbers where each term after the first is found by adding a constant difference to the previous term. Okay, so maybe they start with a problem, a term like 4. This first one has to be given. I don't know how well you can see that. Maybe I'll go with the white. Okay, after that, maybe you get 7, 10, 13, ... 4 is the first term. That constant difference here is a positive 3. It could be going downhill if they started with maybe 7, 3, -1, -5, ... 7 is my first term. This time the constant difference is -4. Okay, a geometric sequence is a step harder, which makes sense because geometry is a step harder than arithmetic, even though this is called arithmetic. So geometric is going to be a little bit harder. This time, instead of adding and subtracting each time, we get it by, oh, I hate when that happens. We get it by multiplying. Okay, so maybe the first term is, not even letting me select the pen. Okay, maybe the first term is 3. What is that constant multiplier? Well, what am I multiplying by each time? Times 2, times 2, times 2. It is 2 here. It could also be called the constant ratio. Sometimes it's usually pretty easy to tell if something is geometric because it's going to get larger much quicker than arithmetic. Because of the constant increase here, this is not going to be a step problem. It's going to be big jumps and bigger jumps and then bigger jumps. So if you can notice it's geometric and you want to find that constant ratio or multiplier, if you just take 48, divide by 24, any term, and then divide it by the one in front of it, you will get your constant ratio. Okay, here are some formulas and you need to know them. This is recursively. Recursively is very, very easy to write a geometric sequence. Still has 4 steps, just like before. First term is x here. The mystery term is the one before it times r. Okay, you could technically write g sub n minus 1 times r like this. It just looks nicer when you put that in front. So that's what they did. R times the one before it for integers n greater than or equals 2. This is the same as arithmetic. This is the same as arithmetic. The only difference is instead of saying plus d, we are multiplying by r. Okay, here is the explicit formula, and there's no way around this. You just have to memorize it. If you recall, for arithmetic, this is just a little review. The formula was a sub n equals a sub 1 plus n minus 1 times d, and that d needed to be distributed, okay? Here's the new one, the mystery term, and this time you can find whatever one you want, is the first terms times r to the n minus 1. This n minus 1 will always be there. Okay, so go back to the one we just had. Where is it at? 3, 6, 12, 24. 3, 6, 12, 24, 48. ... If I'm going to write this, what would I have? Oh, I think green was better. Okay. G sub n equals, what was the first term? Well, that's 3. What is r? I'm multiplying by 2 each time, and it's always, always, always to the n minus 1. 3 times 2 to the n minus 1. So if I want to know what is the 10th term of the sequence, it'll be 3 times 2 to the 10 minus 1 is 9. 2 to the 9th power. 512 times 3, 1536. So g sub 10 is 1536. This is also nice if you remember explicit formulas. You can type right into your calculator and you can generate a table of values, which is very helpful. So let's look at some of these. Let's go ahead and write down the formula. G sub n is g sub 1 times r to the n minus 1. Give the first terms of the geometric sequence described. Okay, the constant ratio is -5 and the first term is -5. So we're going to start with -5, and each time we're going to multiply by negative 5. So negative 5 times negative 5 is going to be obviously positive 25 times negative 5, negative 125 times negative 5, 625 times negative 5, negative 3,125. Okay, notice that it's alternating. This doesn't happen with arithmetic sequences. The reason it does with a geometric sequence is because you're multiplying by a negative and it will change that sign value. Okay, what if the constant ratio is square root of 2 and the first term is square root of 2? Okay, square root of 2 is my first term. After that, we have root 2 times root 2, which becomes positive 2, because that would be root 4, if you guys remember. Root 2 times root 2 is the square root of 4, which is 2. Then I'm multiplying by root 2, and I get 2 root 2. Then I take 2 root 2 times root 2 again, and I get 2 root 4, which is 2 times 2, which is 4. And then 4 root 2. Okay, let's find the first 5 terms of the sequence. Well, I'm going to erase my work over here. What is g sub 1 going to be? G sub 1 will be 2 times negative 0.1 to the 1 minus 1, which is 0. Anything to the 0 power is 1, so that's 2 times 1. The first term is 1. You have a couple of options here. You could go G2 and then plug that in. That's 2 times negative 0.1 to the 1 power. 2 times negative 0.1. Oops, that's not what I put. Negative 0.2. Or you can realize, well, this is my ratio. I'm just going to multiply by negative 0.1 each time, which is what I'm going to do. And the next time I get positive 0.02 times negative 0.1. I get negative 0.002. And the next one's going to be positive 0.123. Is that right? 2. Okay, this is written recursively. Same type of thing. The first term is negative 2. What am I multiplying by each time? 3. Negative 2 times 3 is negative 6 times 3, negative 18 times 3, negative 54 times 3, negative 162. Okay, this really shows if you understand these formulas and how they work in sequences. This time we're going to write 2 rules, a recursive and explicit. Let's do recursive over here. The first term is 12. The mystery term is the one before it. And what do we do each time? Well, it's getting large very quickly, and it's automatically going to be geometric if you see this alternating flip-flop. Okay, and what am I multiplying by? Well, negative 36 divided by 12, negative 3. Make sure, check on the next one. If I multiply times negative 3, am I getting 108? And the answer is yes. You can put that r in front. G, the one before it, 4 integers, and greater than or equal to 2. Okay, explicitly, the formula is g sub n equals g sub 1 times r to the n minus 1. So g sub n equals, what is the first term? 12. What is the ratio? Negative 3. Make sure that's in parentheses, to the n minus 1. Okay, next one is a little tricky for some people. The 3's stay the same. What am I multiplying by? It's kind of even. 4 to 16, I think you can see the 4 here. Multiplying bottoms by 4 by multiplying the tops by 1. So what I'm actually have here as my r is 1/4. I'm multiplying by 1/4 each time. First term is 3/4. The mystery term is 1/4 times the one before it. How do I say the one before it? G sub n minus 1. Finish it up. 4 integers and greater than or equal to 2. Explicitly, g sub n is, what is the first term? 3/4. What is that ratio? 1/4. Always will have the n minus 1. Okay, here's a word problem. After each bounce, a ball reaches 80% of its previous height if it is originally dropped from a height of 6 feet. So we're starting here at 6 feet. You drop the ball. How high will it bounce after it hits the floor the 6th time? I always draw pictures on this because I get mixed up. Here's the first bounce. Where is it at? It goes to 80%. So I take 6 times 0.8 and I get 4.8 feet. After the second bounce, 4.8 times 0.8, 3.84 feet. I'm going to draw my picture first. 1, 2, 3, 4, 5, 6. I think that's right. Is that right? The first bounce, second, third, fourth, fifth, sixth, and where's it at here? That's what I'm looking for. Okay, so 3.84 times 0.8, 3.072 times 0.8, 2.4576 times 0.8, 1.96608, and the last one times 0.8. Get 1.57284 feet. They want it to the nearest hundredth of a foot. Okay, 10 hundredths. Here it is, 1.57 feet. The population in a certain, there will be a question like that on your test and quiz, by the way. I remember. Okay, the population in a certain county approximately doubles every decade from 1950 to 2000. If there was 1650 and 1950, how many in 2000? I'm going to make a table. 1950, there were 1650. 1960, that's what a decade is. It's going to double. 1650 times 2, looks like 3,300. The 70s, 6,600. The 80s, 13,200. 90s, 26,400. And in 2000, we are at approximately 52,800 people. I'd buy a house in this place, man. I bet their housing is really good. Okay. And that's it for today. I hope you enjoyed this. It should be pretty easy, mostly review, and I will talk to you later. Thank you.